Hey, it's Tim the Tutor with Free Test Prep Online, and in this video I'm going to cover Newman projections. Not only how to understand what they are and how they look, but how to convert them to and from skeletal structures. So what is a Newman projection? A Newman projection is a representation of a molecule where the observer is looking lengthwise down a specific bond. The atom in the bond that is closer to the observer is drawn at the center of the Newman projection, while the atom that cannot be seen, because it's directly behind the first atom, is represented by a circle behind the front atom. Here we can see a ball and stick model of a molecule. I placed an eyeball directly in line with that carbon-carbon bond. So from the perspective of that eyeball, how does it look? Well, we can see here that the carbon closest to the eyeball is in front, and we can't see the carbon in the back of it. What you will see, however, is that from that perspective, on that front carbon, we have the white atom on the top right, the green atom on the top left, and that orange atom going downwards. Likewise, on that back carbon, the white atom is going straight up, and the orange one is going down to the right, and the green one is going down to the left. That perspective is easy to see on a ball and stick model. What if we changed it to a skeletal model instead? Here we have the same general idea, except now we have wedges and dashes. A wedge means that an atom is coming out of the screen towards you, and a dash means it's going back behind the screen away from you. But from the perspective of that eyeball, a wedge means that it's going to the right of the eyeball, and a dash means that it's going to the left of the eyeball. On that front carbon, since the hydrogen is going up and it's on a wedge, it's going to be going up and to the right on the Newman projection. Since the chlorine on the front carbon is going up but backwards, it is up to the left on the Newman projection. And since the fluorine is going down, from the perspective of the eyeball, it's just going to be going down. We can see that the back carbon, the one that is blocked from view from the perspective of the eyeball, we can see that that is drawn as a circle. Coming off that circle, we have the hydrogen, which is just going up, and then we have the fluorine, which is on the bottom right because it's on a wedge, and then we have the chlorine, which is on the bottom left because it's on a dash. We call this conformation staggered because the atoms on the front carbon are rotated 60 degrees from the atoms on the back carbon. We can also draw this molecule eclipsed, and you can see that we have the atoms on both the front and the back carbons. We see that they line up directly with each other, and that is a source of strain for the molecule. And it's really easy to see that strain when we have those atoms lined up on a Newman projection. Going from a skeletal structure to a Newman projection depends on the perspective of the eyeball. In other words, it matters which bond we're looking lengthwise down. In the examples above, we placed the eyeball on the left, which meant that wedges were on the right and dashes were on the left. However, if the eyeball were placed on the opposite side of the molecule, then the back carbon would now be the front carbon, wedges would be on the left, and dashes would be on the right. Learning how to think about how a structure is viewed from different perspectives can be challenging at first, especially when you have to think about 3D objects that are drawn with lines, wedges, and dashes. Therefore, rather than trying to jump immediately from a skeletal structure to a Newman projection, it can be easier to think about an intermediary view known as a Sawhorse projection. Instead of rotating an object a full 90 degrees to get to the Newman projection, a Sawhorse projection only partially rotates a molecule. When looking at the leftmost representations depicted above, imagine swinging carbon 1 towards you. That will put carbon 1 closer to you and carbon 2 further from you relatively. Any atoms on wedges will now also be on your right, and any atoms on dashes will be on your left. You can see that in the Sawhorse projection above in the middle. Complete the rotation to turn the Sawhorse projection into the Newman projection, as shown on the right. Now that you know more about Newman projections, let's make this video a little more practical. How do we convert from a skeletal structure to a Newman projection? Well, this depends on your perspective. If your perspective is left to right, that is, the observer is to the left of the specific bond being viewed, we're going to follow these steps. First, we're going to put the carbon on the left in the front, And all we're going to do right now is put a dot as a placeholder. Then we're going to put the carbon on the right as a circle surrounding that dot. After that, we begin attaching the groups bonded to those two carbons. Anything that is up stays up, and anything that is down stays down, whether that be straight up and down or angled up or angled down. Then we're going to attach anything on a wedge to the right side and anything on a dash to the left side. If the perspective is right to left, then we simply reverse what we do. We put the carbon on the right in the front, and we put the carbon on the left as a circle. Then when we attach the groups, up still stays up, down still stays down, but anything on a wedge is now going to be on the left, and anything on the dash is going to be on the right. I know that was a lot, so let's use a practical example to show you how actually simple this is. So we're going to convert the skeletal structure depicted here to a Newman projection looking down the bond from C2 to C3. In other words, we're looking at it from the left-hand side. First, let's draw our perspective. So I'm going to draw a little eyeball over here, and we're going to say we're looking down this C2, C3 bond. Now we're simply going to follow the instructions. We're going to put that carbon on the left, that C2 carbon, in the front, and I'm going to put a dot here as a placeholder for now. The carbon on the right, or C3, is simply going to be the circle surrounding that carbon. Now we can start attaching the groups bonded to those two carbons. What do we have coming off C2? Well, going down is going to be a fluorine. On the wedge, we have a hydrogen, and that is going upwards. On the left, or on the dash, we have a methyl group. So that's going to be going up and to the left. Now, what do we have coming off of C3? Well, it looks like up, we have a hydrogen. On a wedge, going down, we have an NH2. So we're going to put that on the right. And on a dash, going down, we actually have a purple group. So there we have it. There is the Newman projection looking down the C2-C3 bond. Now let's talk about how to convert from a Newman projection to a skeletal structure. We don't need to worry about perspective this time, because we can draw it however we want to. So the process is going to be the same in every situation. To make it simple, we're simply going to put the front carbon on the left and the back carbon, or the circle, on the right. Then we're going to begin attaching the groups bonded to those two carbons. Again, anything that is up stays up, and anything that is down stays down. We're going to attach anything on the right side of the Newman projection as a wedge, and anything on the left side of the Newman projection as a dash. So let's go ahead and convert the Newman projection depicted here to a skeletal structure. We're going to start by putting the front carbon on the left and the back carbon on the right. So in other words, we're just going to draw a somewhat horizontal line here. Let's focus on the carbon on the left now, or that front carbon. Going straight down from it is an ethyl group. So we're simply going to draw an ethyl group, not on a wedge or a dash, but we're simply just going to draw it as that straight line. The left side, we have a methyl group going up. So we're going to draw this on a dash. And of course, on the right side, we have a hydrogen. So we're going to draw this going up and to the right on a wedge. Now let's focus on that back carbon. On the back carbon, we have an OH group going up. So we're simply going to draw that going up off of this right-hand side carbon. We have a chlorine on the right, so we're going to show that as a wedge. Then we have a hydrogen on the left, so we're going to show that as a dash. And notice in our skeletal structure, what is up stayed up, and what is down stayed down. Anything on the right-hand side of the Newman projection is now on a wedge in our skeletal structure, and anything on the left is on a dash. If you got something out of this lecture, please feel free to like this video and subscribe to this channel. If you have any questions or comments, leave a message below. And last but not least, if you want more help or want easy access to valuable organic chemistry resources for free, be sure to check out the notes underneath this video, with a link to join our community.